Okay, a particle moves through a vector field F along C. What does the following integral represent? We've got the integral over C of F dot T ds. Obviously, it must be some sort of line integral with respect to arc length. But it's actually much more than that because of the dot product in the integral, F dot T. So you have to imagine F is a force field, and we have a curve, C, that some particle is traveling along, and T is its unit vector in the direction of motion, its unit tangent vector. Then what does F dot T represent? F dot T represents the amount of force exerted by F in the direction of motion. It's the scalar component of F in the direction of T, which is in the direction of motion. You can prove that by going back to a formula from the very first chapter, where we talked about the vector projection of U onto V. In this case, it would be F onto T. And you could use that formula along with the fact that T is a unit vector to show that the projection of F onto T, the length of that vector, is just F dot T. And so F dot T represents the amount of force exerted by F on the particle traveling along the curve C, that amount of force in the direction of motion. And so if you look at this picture then, if the particle is, say, here, and for the sake of argument, say the vector in red is your unit tangent vector, and this vector here is from your vector field, then the claim pictorially is that F dot with T would be the vector, the length of the vector projection that you get by dropping this perpendicular from the tip of F. Okay, so this vector, oh, what color can I use? Blue. This vector right here, the length of this vector right here is that dot product. Okay? The length of that vector there is F dotted with T. Now, you can verify that with the projection formula if you want to. I'll let you do that on your own. Now, what happens then when you multiply that times ds? Well, that would be a force, right? The force on the particle in the direction of motion times a distance. ds is a tiny little distance. What does force times distance equal, you guys? Work. Yeah. So that's work, which equals work. And so you're summing up all the work done on this particle over all these infinitesimally small pieces of arc length. So what's the integral going to represent? It's going to represent the total work done on the particle in moving through the vector field. So I'll say it this way. The total work, it's the total work done in moving the particle from, let's say, A to B, if in the picture A is the starting point and B is the ending point. The way we've thought of it here, this would be the total work done in moving a particle by the vector field in moving a particle along that path. It doesn't have to represent work done if F is not a force field. So we define more generally the line integral of a vector field, let's call it. So here we go. The line integral of a vector field. So it's going to look the same, but we're not going to call it work necessarily unless F is a force field. So it's the integral over c of f dotted with t ds. But guys, that's not going to be the calculation formula. It's just symbolism. So what's the calculation formula going to be? Well, okay. If you can parameterize c, then the limits will be the t values that produce the beginning point and the end point on the curve. And then you could think of t. Do you remember what t is? Remember, it's r prime of t divided by the magnitude of r prime of t. Remember that? That ring a bell? But then what is ds? It's magnitude r prime of t dt, isn't it? So I replaced t with what it's equal to, r prime divided by magnitude r prime, and I replaced ds with magnitude r prime of t dt, the same ds from the arc length formula evaluation we did earlier. So from this we can get an evaluation formula. The first thing I notice is if you cancel the magnitude r prime, you get a nice integral in terms of t. You get f dotted with r prime of t dt. This is important for calculation purposes. This is what we use to calculate. But then there's one more bit of symbolism that we end up using that you need to know about. And some of the symbolism gets a little irritating because there's so many different ways to represent the same thing, but you need to know about it because you're going to see it written this way in your book and many other books. This r prime is a vector, right? If r is a vector, then r prime is a vector. So this is a vector differential. So think about it. In Leibniz notation, the derivative of the vector function r with respect to t in prime notation is r prime of t, right? So if you play with the differentials here, multiply both sides by dt, dr is equal to r prime of t dt. And so what a lot of books will do for symbolic purposes is replace in the calculation formula r prime of t dt with just the vector differential dr. So you're going to see the notation, the integral over c f dot dr. And so all of these mean the same thing. The integral over c of f dotted with t ds means the same thing as the integral over c of f dotted with dr. The only one of these that's a calculation formula is this middle one. So that's why I circle it. You just have to realize the other ones are telling you, oh, line integral of a vector field. Okay? This guy is the important one because it tells you how to calculate. Okay, you guys, a couple of quick notes before we do an example. Note number one, when you integrate over a vector field, the orientation of C matters, and that's because if you remember the original formula I used to conceptualize the integral over a vector field, remember it was f dot t, where t is the unit tangent vector, ds, right? But if you parameterize it, so C is parameterized one way, right? But let's say you integrate in the other direction, you parameterize it the other way. Then t becomes negative t if you start going the other direction. And so you get the opposite. You could pull this negative out. You'll get the opposite answer that you'd get going in the other direction on if you had a reverse orientation on C. Okay? So orientation matters. And if you integrate, well, note number two actually tells us symbolically what happens. If you integrate over negative c of f dot dr, in other words, if you take the line integral over the vector field and you're integrating over c, or in this case negative c, then the value of that integral is going to be the opposite of what you would get if you integrate over c. Compute the line integral of the vector field f equals 4x 3y over the quarter circle part of x squared plus y squared equals 4, oriented counterclockwise in the first quadrant. Okay. So what does that look like? Let's draw that curve. So if we draw that curve, let me throw in what that curve might look like. Give me just a second here. Change the color. Okay. So the quarter circle in the first quadrant, what would the radius be? Radius 2, right? So the quarter circle might look something like this. Let me do it in red. In the first quadrant. And I told you in the problem that I want it oriented counterclockwise, so there's your orientation. Okay, so we're going to integrate over this curve. This is C. So how do we do it? Well, you've got a lot to remember. You've got a lot of formulas to remember. And we up the ante in this chapter, so what do? Well, you remember particular versions of the formula. For instance, symbolically, we're asked to compute the line integral. Symbolically, here's some common notation for that. The line integral over C of f dot dr would be the line integral of this vector field. Okay? And then you have to remember what's what. What's the computational formula? The computational formula tells you what you need to find. So the more important formula to remember then is that this line integral is equal to the integral from a to b of f dot r prime of t dt. This formula on the right here is the computational formula. And it tells you what you need to find. It tells you that, well, you need to find r prime of t. In order to find r prime of t, you need r of t. So you kind of work it, the symbolism from inside out. You need r prime of t. Also, to get this integral in terms of t, you're going to need f in terms of t. But you can't do anything until you get this curve C, until you write that as a parameterization. Okay? Now, so let's talk about that. So let's parameterize x squared plus y squared equals 4 in the first quadrant. Now, there's a trick for doing this. You may or may not remember it. One way to help you remember how to parameterize any circle or any ellipse is to write the equation in the standard form of an ellipse, not a circle. To write this equation in the standard form of an ellipse and get 1 on the right-hand side, what could I do? Divide both sides by 4, and then I get x squared over 4 plus y squared over 4 equals 1, which is the same as x over 2 the whole thing squared plus y over 2 the whole thing squared equals 1. And then you use your old friend, the trig identity, cosine squared t plus sine squared t equals 1, right? So in that scenario, what's acting like the cosine of t? What are you squaring first? X over 2, right? And what's acting like the sine of t? Y over 2. So you could set, to get your parameterization, you could set x over 2 equal to cosine of t and y over 2 equal to the sine of t. And get x equals 2 cosine t, y equals 2 sine t. Now, you may recall then that the parameterization is automatically counterclockwise as desired, but if we only want to curve out the quarter circle in the first quadrant, what is t going to have to range from? 0. Think about it. If you plug in 0 in for t in both this little parametric equation and this one, you'll get 2 here because cosine of 0 is 1 times 2 is 2. You'll get 0 here because sine of 0 is 0 times 2 is 0. So you will get this point, won't you? And that's where you want to start at. Okay? And then if you plug in, okay, t ranges from 0 to, must be pi halves, right? And you want to end up here. When you plug in the last value of t, you want to end up there. And you do, because when you plug in pi over 2 for cosine, in for t, in the cosine function, you do get a 0 there, don't you? So you want, this is the point 0, 1, you want this coordinate to be 0, which is exactly what x gives you when you plug in pi over 2. And you want the second coordinate to be 1, which is exactly what this parametric equation gives you when you plug in pi over 2 for t. Not 1, I misspoke. It would be 2, wouldn't it? Because when you plug in pi over 2 for t, you do get sine of pi over 2 is 1 times 2 is 2. So you do end up at in the right places when you plug in the endpoints. That's important. Okay? And then of course you know these parametric equations will carve out this circle because they satisfy this equation. Question, yeah. Yeah. Thank you. Yep. 2, 0, and 0, 2, right? Okay. Okay, so how could you write this in terms of r if you want to write it that way? A vector valued function, it's just 2 cosine t, comma, 2 sine of t. Okay? All right, so you've got r of t. So what does your calculation formula, this guy, tell you need to do? Tells you need to take the dot product of f with r prime. Remember, f has components 4x and 3y. So if you take the dot product of f, which is 4x comma 3y, with, oh, we need to do that with r prime though, don't we? So I almost skipped that step. What is r prime? What's the derivative of this guy? Negative 2 sine t. What's the derivative of this guy? 2 cosine t. Okay. So this formula up here tells us we need to take f and dot it with r prime to get our integrand, essentially. Okay. So that's what we're doing, you guys. So I'm taking f and then I'm dotting that with r prime. Does that make sense? So this is our integrand. This is going to be f dotted with r prime, in case you're wondering what the heck we're doing. Okay? So what is that? You remember what the dot product is? So you multiply the first components together. What does that get you? Negative 8x sine of t. Multiply the second components. What does that get you? 6y cosine t. Then what do you do with those? You add them. You get a single scalar function for your integrand, which is what we want. Now we do need to get it all in terms of t, so what's the problem? I see an x and a y, right? But wait a minute. Go to your parametric equations or your parameterization, either one, and it tells you what x is, right? X is 2 cosine, y is 2 sine. So down here we can fill in, for x we can fill in 2 cosine of t, for y we can fill in 2 sine of t, and when the smoke settles, what do we end up with after doing the multiplication? So what, negative 16 sine t cosine t plus 12 sine t cosine t. But those guys are like terms. So what do we have when we add them together? Negative 4 sine t cosine t. So to me, you guys, that's the hardest part. But it's formulaic. If you know the formula, it's just a process to go through to get that integrand. F dotted with r prime. That's what you got to remember. Now, when you set up the integral then, remember generically the formula is the integral over, well, once you set up in terms of t, you can say the integral from a to b, f dotted with r prime, and then everything's in terms of t. So I left off the function notation, right? So that's what we just found. That integrand, f dotted with r prime, in terms of t, that's what we just found. So when you set it up then, you get the integral from, okay, the a and b are the limits on, well, the limits on t that give you the beginning and ending point of your parameterization. So the lower limit in this case should give you this point, 2, 0. And the upper limit should give you this point on your C, right? And it does, as we already discussed. Okay. So we fill those in. What were they? If you go back, it was 0 to pi halves, wasn't it? So 0 to pi halves. And then -4, is it okay if I put the -4 on the outside? And then just make it sine of t, cosine t on the inside. Does everybody see what I did there? dt. Now at this point, it's a calculus 1 type integral. Well, actually calculus 2, I suppose. Because what kind of trick are you going to have to use on this to integrate it? Substitute. So what's u in this case?
Sine t.
U is sine of t, so your perfect du is right there. Du is, if u is sine t, what's du? Cosine t. So do you actually need to make the substitution? There's u, and that whole thing right there is du. Right? So everything's perfect. You don't need to multiply by a factor and divide by a factor. It's good to go. So if you integrate u with respect to u, you get u squared over 2, but if we don't actually make the substitution, what does that become? -4 out front still. It becomes sine squared t over 2, right? Evaluated from 0 to pi halves. Everybody see how I got that? That's like the sine squared t over 2 is like your u squared over 2. But then you can pull that 1/2 out front, multiply it times the -4, and what do you get? -2, and then sine squared evaluated from 0 to pi over 2 is just what? 1 minus 0, right? Because if you plug in pi over 2 to sine of t, you get 1 squared is 1. If you plug in 0, you get 0. Remember, I already pulled the 2 out, so we're not dividing by 2. So you get just -2.